my name is Hania Abdul Basir, and today I will be presenting my project titled Adaptive Loss Function Design in Multitask Graph Neural Networks for Materials Discovery, supervised by Dr. Henry Lee. It has become increasingly important to address the rising demand for energy while mitigating the risks of climate change. Among the renewable energy sources, wind and solar have been predicted to increase in use by 2050. But these renewable energy sources have an intermittent power generation, which requires efficient renewable energy storage. Existing storage methods require costly electrochemical reactions dependent on catalysts. Density functional theory simulations are useful in finding such new catalyst structures. However, these simulations are computationally intensive, costly, and time-consuming. Graph neural networks can be used to accelerate the simulation process of DFT. Before I go further, let's look deeper into some of the main concepts around my project, starting with density functional theory. Density functional theory, also known as DFT, is a quantum mechanical computational modeling method to study the electronic structure of molecules and materials. DFT is used for discovering and evaluating new catalytic materials by investigating the activity and sensitivity of the catalytic structures. DFT calculations are computationally intensive, which is why it limits their application for scalable and efficient solutions. What are graph neural networks? Graph neural networks, also known as GNNs, are a type of neural network specifically designed to operate on graph structured data, where its nodes represent the input data points and edges represent the connection between the data points. This structure enables GNNs to perform prediction tasks at the node level, edge level, and graph level. One of the key operations of GNNs is pooling. Pooling aggregates features from multiple nodes into a single node, typically using a sum operation, enabling more informed predictions by considering graph connectivity. It allows multiple nodes to be combined into a single node with aggregated features. Another key operation of GNNs is message passing. GNNs employ message passing to propagate information between nodes in a graph, allowing each node to gather and update its representation based on its neighbor's information. In message passing, node embeddings are first gathered from neighboring nodes, then they're aggregated using a function like sum, and then the graph is updated with new information. Now let's talk about the OC20 dataset, which is used in my project. The OC20 dataset by Chenosud et al. In 2021 is a comprehensive dataset created for the Open Catalyst project, OCP. It is an open source project with a dataset containing around 1.3 million unique structures, and it is designed for the study of machine learning approaches for catalyst discovery. It applies graph neural networks like CGCNN, SCHNet, and DimeNet++ as baseline demonstrations. A main challenge of efficient DFT approximation described in OCP is a fundamental calculation called structural relaxation. Structural relaxation is used in studying a structure's activity and sensitivity. In this slide, you can see a visualization of the initial, middle, and final steps in the structural relaxation trajectory from the OC20 dataset. S2EF task predicts the energy and force of a system as calculated by DFT and uses the system's atom positioning as input. Existing solutions for the S2EF task are available, but none can accurately predict both energy and force simultaneously. S2EF is the most general task out of the three tasks described in the OC20 project, which can be applied to many catalysts and related studies. Now, to summarize the motivation of my project. Efficient DFT simulations are required to address the challenge of renewable energy storage. Efficient DFT calculations can be tackled by three tasks: S2EF, IS2RS, and IS2RE. S2EF is a multitask problem, and existing solutions for this task require using two separate models, which is time-consuming and less efficient. It requires two separate models so that the first model can only evaluate energy and the second model can only evaluate force. The main aim of my project is investigating a solution to the S2EF task using the grad norm algorithm to dynamically tune the weights of energy and force in the loss function of a graph neural network to predict the force and energy of a system simultaneously without needing to use two separate models. Now let's move on to the methodology of my project. Two models were used in my project, one containing fixed weights for energy and force, and the other model using grad norm algorithm to dynamically tune the weights of energy and force. SCHNet was used as the GNN model where the learning rate was set as 0.0005 and the total epochs was 100 and the initial energy and force weights were set as 0.5. And baseline function was the L1 loss using sum as the reduction method. For my dataset, OC20 200K training set was used with a sample size of 50,000, which was split into training, validation, and testing sets with a ratio of 80, 10, 10 respectively. For evaluation, mean absolute error was used of both the energy and force predictions against the energy and force obtained from DFT calculations. Average MAEs were obtained from 3 different tests for each model with different seeds. Here is a list of all the libraries and their versions that were used in my project. And for hardware, a NVIDIA GPU available on the university server and MacBook Pro were used. And Visual Studio Code was used as the code editor. For the model using fixed weights, an existing L1 loss function was used off the shelf, and for the model using grad norm, L1 loss was also used as the baseline loss function, and the weights were dynamically tuned using the grad norm algorithm. The grad norm algorithm was implemented using the pseudocode from the paper by Chen et al. In 2018, which is shown in this slide. Now, this slide shows the average MAE of the energy and force predictions obtained from the both models, and it also shows the energy loss curve obtained by the model using the grad norm algorithm, and also the force loss curve obtained from the model using grad norm. Energy and force MAEs were higher in the model using grad norm than the model using fixed weights. Energy and force decreased as the number of epochs increased in the model using grad norm. A decreasing curve of energy and force loss is a positive sign as it shows the decrease in disparity between the predicted energy and force and the actual energy and force of the system obtained from the DFT calculations. Energy and MAE results could be improved by investigating different model architectures, optimizers, and hyperparameters. However, this could not be done due to time constraints. Hence, I was only able to focus on implementing the loss function and tested the implementation once without changing other hyperparameters to find the optimal values. For future work, if I had another 6 months, I would retrain the models but store energy and force weights to see how they are updated. I would investigate using baseline loss function of L1 loss with mean as the reduction method. I would also conduct more tests to find the optimal hyperparameters and model architecture to integrate the grad norm loss with, for example, values for learning rate, batch size regularization, parameters, dropout rate, and optimization algorithms. In conclusion, increasing demand for energy and the need for renewable sources like wind and solar require efficient energy storage due to intermittent power generation. Simulations like DFT are useful but computationally intensive, costly, and time-consuming for evaluating catalyst structures. Graph neural networks can automate the simulation process to expedite catalyst discovery for energy applications. The project investigated the solution to S2EF task using the grad norm algorithm but did not find improved results when compared to using fixed weights. Thank you. And these are my references.